Hello, this is Nice Micro, and in today's programming tutorial we will be looking at the implementation of a Swiss tournament in Godot in GDscript. If you already know what the Swiss style tournament is, you can jump ahead. I will have timestamps down for you. And if you are not really interested in the GDscript, the Godot implementation, I think this video could be interesting for you still, because I will give you a detailed explanation of the algorithm using just simple natural language. And GDscript is very similar to Python, so you will be able to use it if you want to implement it in Python. I used the GDscript and the Godot game engine here because I wanted to create a system which gives me a presentable UI directly based on these results without having to put in too much effort. So let's take a look at what types of tournaments there are and how the Swiss system is compared to those. So simplest one is a single elimination system, in which basically everyone who loses a game will be eliminated and the winners will be paired again, and if you lose you get out, and then the winners will play each other until in the end we end up with two players remaining who will play a playoff or a final in the end, and the winner of this final match will be the winner of the tournament. Another way to do a tournament is a round-robin system where everyone plays everyone, so you will have results which will tell you like the exact ranking, like how each players are ranked or each teams are ranked versus each other. But this is a very long system with a lot of games that you have to play, and it might end up in a situation where the last few games will not really have any big impact on the final ranking, so it won't be interesting for the viewers and the players either. So of course you can do some kind of multi-stage tournament, which is often how World Cups, for example the soccer or football World Cups, are organized, that you have group stage, and inside the group everyone plays everyone, and whoever gets into the elimination stage, they will play single elimination. When one loss will get you kicked out from the tournament. The double or triple elimination system is kind of a refinement of the single elimination, so you don't want to have like a round robin or a group stage, but you don't want the players to be eliminated when they lose a single matchup, so you will let them lose once. In double elimination you only get out or kicked out when you lose twice. In triple elimination you only get kicked out when you lose 3 times. And of course we also have the Swiss system, which is most often used in chess tournaments, but nothing limits it to chess. You can use it to any type of tournament. In the Swiss system, the basic idea is that you are trying to match people with similar scores. So the people who won all their matches previously will be playing with each other. The people who lost all their matches before will be playing with each other, and the people who lost 2 matches and won 2 matches will also play against other people who has the same score, or at least we try to find a minimal difference. And as long as possible, 2 players don't play against each other twice, so we don't want rematches, because that would make everything too long. And this way we can end up lower number of matches than round robin, so we won't really get into a situation when it is not possible to have 2 players play a matchup, because basically so the number of matches will be lower than if everyone played versus everyone, so we don't expect 2 players have to play each other twice. The other good thing about the Swiss system is that no one gets eliminated. Everyone can play the number of rounds that have been pre-assigned. So for example, if you have like a tournament where people have to like travel to your location to participate, and they would just get eliminated in the first round, then they would feel like the whole trip did not worth it. But in the Swiss system they will keep playing until they play their number of rounds, and because they are generally playing versus other players who have the same record than they have, the opponents have similar skill levels, so the matches will be more interesting for the players and hopefully for the viewers also, if you are having viewers on the tournament. The problem with this system is basically that every game has to finish in a round before anyone knows who their next opponent will be. So if there is one round that lasts very long, the two players have a hard time figuring out who would win. Then everyone else has to wait, and they will not know who their opponent is until that point, which you can also count it as a benefit that everyone figures out who their opponent will be at the same time, so no one gets an advantage based on just based on who finished their games before. A naive way to implement the Swiss system would be to order the players based on points, so highest points get to the first place and the lowest point get to the lowest place, and then just try to pair them up, like the first player with the second, third with the fourth, and fifth with the sixth one. But of course you have to make sure that there are no rematches, so maybe if the first player already paired with the second one, then you pair the first with the third one and the second with the fourth one. But this way you will have a hard time finding a good solution after a few rounds based on the number of players who have already played against each other. So I think it is a easier way to approach this as a kind of finding a minimum. So we are going to calculate all possible point differences for each pairs. So each player versus each other player, we will get a point difference, and then we will try to find all possible pairings and calculate the sum of these differences. So the higher point sum rather you would get for a list of pairings, the worse it is. So you want to find the minimum. It's kind of a minimum search approach, and then you will find that lowest sum difference pairing. This will always end up finding you the best solution. The problem is that the number of possible pairings is on the order of the factorial of the number of players. So it gets really big really quick, and our computers are very fast but are not infinitely fast. So maybe if you have more than like 16 or 20 players, you will have a problem trying to make like an exhaustive search finding all possible pairings. So how I would approach this is having a function that gets all the players and the point matrix, which contains all the points for all the possible pairings, and the limit value. So we will use limit value, trying to ignore pairings that would include like ridiculously high points for pairing. So if any kind of system would have like the worst player matched with the best player, we'll try to kind of ignore that. And I will also just use this point matrix to indicate players who have played against each other. So I won't take a look at every time at whether they played against each other. If they already played against each other, they will just get ridiculously high point. So the system will default to avoid making that pairing. So if we want to implement this, I would write a function in which there is a trivial solution. So the trivial solution is, of course, when we only have 2 players on the list. If you have only 2 players on the list, then the only possible pairing is just these 2 players playing against each other, and the point you would assign to this is just the corresponding point between these 2 players. But otherwise, if you have more than 2 players, so in this case we have more than one possible pairing, so we will create a list for these pairings which will we populate. We will go through each player in the list except for the first one, because we are going to find a partner for the first player, and if the point for the current player versus the first player is higher than the limit, we will just jump to the next player. We will ignore that. But if it's not higher than the limit, then we will create a duplicated player list. So you want to duplicate the player list because both in GDscript and in Python, lists or arrays are handled dynamically. So you don't want it to be don't want your original player list to be modified. So you create a duplicate of this player list, and then from this player list you remove the first and the current player. So these 2 are paired versus each other. So we want to have a reduced list which will give us all the possible pairings without these two. So these two are already paired, and everyone else, we want all the possible pairings. And we will collect all these possible pairings in an empty list, and just for easier. So basically you could use this green list here instead of the red directly, I think, but I think it's easier to understand what's going on if we use the red one. So what we will going to do is we will just recursively call this function with the truncated player list. So now we selected 2 players from this list who are paired, and all the remaining players we will want to see all the possible pairings. So we call this same function again with the truncated player list, and we get all the possible pairings from them. And for all the pairings we get, we just add our current pair with the first and current player and add their point to the sum, and then we will give this to the pairing list, and in the end we will just merge this new pairing list with the full pairing list, and then in the end we will return the full pairing list. There are a few things which we could optimize in this. So for example, when we call the function again recursively, we could fine-tune what kind of limit we are going to use based on what we got back from the previous pairings. So for example, we don't want to have any more pairings that are worse than the ones we've got from here, or something else. Or maybe you don't want to return the full pairing list. Maybe you could just use this function itself to only return the best pairings from whatever it found in this function. But in this case, we are going to return everything. So let's take a look at a test run here, which has 6 players. So A played B, C played D, E played F, and these are the results they played. So they played until 2 victories. A beat B 2-1, and C lost to D 0-2, etc. So we just basically every set they won will give them 1 point. And when we calculate the matrix for the point differences, the people who played against each other will get 100 bonus here. So they are not paired together again. So this way A and B already played against each other, so it's 100, but their point difference is 1, so this is 101. A and C have, so A has 2 points, C has 0 points, so A and C is 2. A and D both have 2 points, so that pair is going to be 0, etc. So when we run our function with this full list and this matrix, what we will do is, so we ignore the first player because we want to find a pair for the first player, so we go straight to the second one, who is B, but A and B has a very high score. This is going to be higher than our limit. Maybe we set the limit to 100, so we are just going to ignore players who already played against each other. So we jump straight to C in the next round, and A and C, that is a 2-point difference, and we will call our function recursively after removing A and C from this function. So we will use these 2 boxes to collect the results here. So let's call the function again with the player list that is truncated. So we only have B, D, E, and F in here. So this is still more than 2 players, of course. So we will ignore the first one and go to the second one in the list. So that is B and D. So B and D pair has like a 1 difference based on our matrix here. So let's duplicate the list. This is definitely less than the limit. We remove B and D from this list and only have E and F. So let's collect the results for the possible pairings of A and F. But of course, when we recursively call this function for only 2 players, then it will just return whatever the pairing has. So the only possible way to pair 2 players is with together, and the sum of the points is just the point this pairing is, which is for the case E and F is 101 here. So once we got it back from this function, we add B and D. So B and D was our pair, and B and D had a point difference of 1. So we add 1 to 101, and this way we got the BDEF pair at 102 points. So next we jump to E after copying this to our green box here. And so B and E is a pairing of 0 points. The point difference is 0, so that is definitely less than our limit. So we will call the function by truncating this list to just D and F. So D and F, of course, is again trivial to find all possible pairings, which is D and F is also 0. So this pair is also 0 points, so that will be returned. We will add B and E to this pairing, and in total it is still 0. So let's add this pairing to our green box here and then move to the player F. So B and F, they also have not played against each other. The point difference is only 1, so this is less than our limit, let's say. So we will call the function again with the truncated list now with only D and E present in the list. So D and E, of course, again, trivial solution, only paired one way, which is D with E, and their point is 1. So D and E is 1, B and F is also 1. So this possible pairing will have a sum of 2. So let's add this also to our green box here. And because we reached the end of the list here, we can just return, this function will just simply return this list to our original function, who will be able to add A and C to this. So A and C was 2. So the ACBDEF pairing will be 104. The ACBEDF pairing will be 2. And the ACBFDE pairing will be 4 points in sum. And of course, these will be just added to the green box. This red box will be emptied. And then we will move to the AD pair. And this one, we are not going to go through manually, but this is basically the gist of how this recursive algorithm works. So now that we've done that, let's just go to Godot directly, how this implementation works in GDscript. This function is going to create the matrix with the point differences between the players, and because our player list here contains the objects, which are like instances of classes for each player, we are just going through the indices here to create a matrix based on these two indices. And as you can see, like in the example, we don't have to have the point difference both for like 1 and 2 and 2 on 1. So here we only go up to index 1 with index 2. So player 1, we will get the points, which basically going to give us the number of victories this player had, and we will add some virtual points here. So virtual points, some variation of the Swiss system, you will assign points to each player even before the first round has started, based on either like previous tournament results or ELO scores or things like that. And usually what happens is that in the first few rounds, these virtual points count as full points, so this will be multiplied by 1. And as the tournament progresses, the effect of these virtual points will be reduced, and in the end, it will be even reduced to 0. So only the score got from this current tournament will count when calculating the differences. So here we can kind of dynamically use like a 0 multiplier here if we don't want to use virtual points, or use the virtual multiplier as 1 if we want to use these virtual points, and any floating point number between 1 and 0 if you want to partially take this number into account. And I named this as a badness point here because the higher it is, the worse it gets. So first of all, if these two players have played against each other, that will be 1,000 points, and if they played against each other multiple times, that will be a multiplicative of 1,000. Because so this is in this system, this is not only for Swiss systems that I developed here. So it is possible that maybe you had some other type of games before the Swiss system started. So there, some of the players might have already played against each other more than once, and those kind of pairings you want to really ignore here. Then we will increment this badness point by actually the square of the difference. So in our example here, we only took the absolute difference between the two, between the points of the two players, but here we are taking the square, and this is because if we have like maybe player A has 4 points, and then player B has 3, and then player C also has 3, and then player D has maybe 2 points. So if we pair A with B and then C with D, this is a difference of 1. This is also a difference of 1. If we just take the absolute values, the sum of this pairing would be just 1. Or 2 rather, 1 plus 1. But if we pair this B with C, that's 0, and then pair with A with D, that is a 2. And that would be also the sum of the differences would also be 2. But I think this second type of pairing would be worse, because there would be a bigger difference between one of the players, even though the other pairing would be almost like a perfectly balanced. I think this is worse. So if we do the squaring, then 1 squared plus 1 squared is 2, but then 0 squared plus 2 squared is 4. So this second type of pairing with BC and AD would be worse. So that's why I use squaring this point difference, but you can do whatever you want in your implementation. And I will also add some more fine-tuning here, because it is possible for multiple player, of course, to have the same point differences, and I want to like give a little fine-tuning here. So this, whatever this is divided by 1,000. You can see this is not going to interfere with the point differences, but will add like a 0.001 or 0.002 or something. And this is based on the index differences. So here index 1 is always larger than index 2, because index 2 only goes up to the range index, which is the highest index 2 can be index 1 minus 1. So we don't need to take the absolute value here. But we divide it by 1,000. And this is basically assumes that the players have been ordered. So the best player is index 0, and the worst player is index n minus 1. And this is what actually happens. So in this case, I can assume this, because this is how my algorithm works here, is always orders. Before calculating these points, we order the players by their ranking, or rank the players. And the ranking is not only based on their scores. So this will be different, because the ranking will be based on both scores and how many matches they lost. So scores only count as for the wins, but they could have lost different number of matches, because if you always play up to 2 victories, you might have won twice, but you either play 2-1 or 2-0, and in that case you could have two players who both have 2 points, but one of them played 3 matches and one of them played only 2 matches. So those kind of things can count in the ordering of the players, or even you can take into account who they played against. So maybe both players have the same amount of victories and losses, but one of them won against higher ranking players and the other one played against lower ranking players. You could also use fine-tuning the ranking, and by giving like a tiny influence from that into this point, that can even make your final pairing of the players a little better. So this is kind of the fine points of the implementation of calculating this match matrix here. And of course, the find all pairing is basically just the implementation of what we've seen in the natural language algorithm that I presented to you. So if the player list only contains 2 elements, so this is less than 2, but we assert that it should be 2 because, well, it says even numbered players should be handled elsewhere, but it's actually odd numbered players that should be handled elsewhere. So at this point we should have even numbered players, and so this remaining players that we get here should be exactly 2 of them. And of course the point that we have to return here is just whatever is in the point matrix for them, and we will return a list here. So this one is only one possible list or one possible pairing, so this will return a list with only one element. This one element is going to be a dictionary. This dictionary will contain an element which is the list, and the list is an array which contains an array of 2 players. So each array in this array should have 2 players. So this is the pairings array, and then points will be just a number, which is the points we got from the matrix directly. And of course, if we have more than 2 players, then we go here. This combo list will be all the pairing combinations will be stored in this array. And well, we go through all the players except for the first one, so this is why it's range 1 to whatever the length is, not range 0, and save the original indexes, which is the index from which we use in the point matrix, and get whatever point these 2 would have against each other. If it's higher than this limit, so this ignore limit, and also it is not, the index is not 1. So if index is exactly 1, so because this function should return at least one possible pairing, what I do here is if it's the first, or rather the first player is paired with the second player, then we don't use the ignore, we go through anyways. You could use something else, so you could do, for example, always, so only not use the ignore if this is the last element and your combo list is still empty. In that case you shouldn't ignore. So that is kind of a different implementation. Maybe that would be more optimal, of course, because in this case, however bad the first and second player's pairing is, it will always be calculated. So here we copy the original list. We do this duplication because in GDscript list is always passed through the functions as a reference. So if we just removed the elements from the player list, that would be forever, that would be final. So we instead create a duplication of this player list, and we will get our first pair, which is the first player and the current player, and remove those from this copied list. So this pop-at will remove those players and we'll just append them to the first pair. And here is the function call back. So this is going to be our recursive function call. We send the copy list here instead of the player list, the point matrix, and the ignore number, the limit is not changed. So you could dynamically change this ignore number here if you wanted to, based on whatever you find, based on like whatever you find in with the previous players, but here we just use the same ignore number, whatever happens. So this one will basically return a list of multiple possible pairings, and we will go through all the pairings one by one, and all the pairings will get into this generated combo list one by one. So what we do is get the list out of this and append the first pair to this. So we already have player 1 and the current player as a pair here added to the other possible pairings, and then the points will be also incremented by the point that this current player and first player had together, and add this to the new combo list, which is collecting whatever is coming from this pairing. And in the end we just add everything from the combo list to the new combo list to the combo list. And here you could basically, if you wanted to, maybe you just want to add the lowest number, so you could just throw away all the higher numbers and just append whatever is the lowest number, and then the end this function would always just return one possible pairing. In my case, I get all the pairings, or except for those that are ignored because of the ignore number. So I get all the possible pairings, and then I use a custom sort function to sort these pairings and find the one with the lowest point in it. So this is basically my implementation of the Swiss system in GDscript. I hope you find this useful, and if you have some ideas how to optimize this further, you can always leave a comment down below, or you can go to my GitHub, where you could find, where is this? Maybe it's in repositories. Yes, in repositories we have Nice Tournament. So you can go to my GitHub, find Nice Tournament, download it or clone it, and maybe you can implement your improved Swiss system and do a pull request with this to my repository, and maybe I will review it. But anyways, any ideas, comments, questions, I welcome them down below. You can subscribe for the channel if you want to see more stuff like this and more stuff like the other stuff that you can find in this channel, and give a like to this video if you liked what you've seen, and I will see you next time. Bye bye.